All right, we'll just have to settle for this. So, hello, great to be here. I'm Christoph. I write a lot of Rust code. I also love NixOS, which is why it was great to see a talk also on Geeks. I'm not quite as deeply entrenched into the packaging ecosystem as a lot of people here. I'm also a stand-in last-minute replacement, so shout out to Rudra, who unfortunately couldn't be here due to visa issues, so I'm filling in. So I do work at Wasmer. We're a company, a startup focused on WebAssembly. We are building a WebAssembly runtime, a package registry, and a compute cloud. And I'm here to talk to you about universal packaging and universal execution of code powered by WebAssembly interfaces. So you're probably asking yourself, universal what? What are you even talking about? So who here has ever maintained a library? Hands up. Who? Yes, pretty much the entire room. Who has had to make a library reusable across different languages? Languages, okay. So pretty 1/3 at least, so that's great. So you'll know what I'm talking about. Just let's look at an example. There's the hash. We're looking at something simple, the hash IDs library. So hash IDs, you've probably seen them before. They're used by YouTube to generate video IDs. They're a way to encrypt numeric IDs into something that looks reasonably nice but can't be reversed. So you can't guess YouTube's internal database IDs. So it's one functionality, it's relatively straightforward, but it's not one library. So there's an NPM library, there's a Python library, a Rust crate, and these are all completely separate implementations. They don't share any code. And we see that happening again and again. Like there's something cool written in one language, you want to reuse it in a different language. So someone thinks, oh, I'll just port it, I'll just rewrite it. And is that good? I would argue no, because A, it's a lot of wasted effort from your maintainers. Like you have to maintain 5 different code bases doing the same thing. And you have to write docs, you have to do maintenance, fix issues. And the bigger issue for users is probably inconsistencies, because like it won't matter that much with a small library with hash IDs. But as soon as we're talking something more complicated, each implementation will have some features implemented, others not. There will be bugs that are different between each implementation, and these always crop up over time and usually lead to bugs in your own code. And also performance. Like one library might be very fast, and you're assuming it will be fast in another language, but suddenly something is very slow. I've run into this particular problem quite a bit. And the last problem from my perspective is usually what happens is you don't just have one alternative, but there will be 3 people implementing the same thing for Python, and then you end up with 3 different libraries. So which one do I actually pick? So how do we currently fix this? And like the only real approach at the moment is to use CFFI. Like you write your code in C, C++, Rust, whatever language where you can expose C bindings from C interface, and then you write wrapper libraries. For NPM, you use the Node API to translate between types, call functions. For Python, there are C types. But what this means is there are quite a few problems with this approach. One is, like, C might be the lingua franca of programming languages. Like, every language interoperates with C, but the C API is very limited. Like, it doesn't represent types in basically any programming language. So you always have to jump through hoops to actually get your types across, to actually make things usable. You also have to compile for each different architecture. Either you do that on demand, like when you run npm install, stuff gets compiled, or you have to distribute artifacts, like with Python wheels. And this ends up being a lot of effort, a lot of complexity in the build tooling, and across the whole ecosystem. And more work and more bugs, because, hey, I need the native library to compile this, but it's not available. Oh, you just need to install it. And I think pretty much everyone has been through that pain. You also need to repeat that work for every language, because every language uses a different interface, and you just have to do something custom. And last but certainly not least, this is very bad for security, because you're loading a native library into your process that can do anything in memory, can do anything with the operating system. You have no control over it. So all vulnerabilities in that C library you just imported, they affect you now. All the bugs can corrupt your memory, and you get crashes. But it's the only real reasonable way how we can approach this problem right now. So no matter if we port or if we use CFFI, it ends up looking something a bit like this. So a patchwork of solutions with a lot of manual work required, and it's just awkward. And that doesn't look like how it should look, right? So can we do better? And I would certainly hope so, because otherwise this talk would be kind of pointless. But so how do we want things to work? How should they work? We want to write our code once and be able to use it everywhere, meaning use it in every language, across the whole entire ecosystem of dozens of languages that people use. And we want to run it everywhere, meaning on iOS, on Android, in your browser, on the desktop, in the cloud. And for this to be interesting and appealing, it needs to be effortless. Like, we need low overhead for the maintainers and no overhead for users. And if we're going to do this, then it would better be secure, and much more secure than the current solution of just loading C libraries. So what do we actually need to make this happen? We need a cross-language ABI. And ABI basically just means how do we represent types in memory, and how do we call functions, and how do we do so between different languages. We need a common secure execution model, meaning a way to run the actual code, and do so in a secure way, and do so preferably with a single artifact. So we don't need to build 5 different things for 5 different CPU architectures or operating systems. And we need really good tooling to make the whole thing effortless, seamless to use, both for the maintainers and for the library users. And so we at Wasmer, here is our approach to how we solve this. And we're building on 4 different components. And we'll go through each of these components, and in the end, I'll show a demo to see how it all works together. And so the components are WebAssembly, WebAssembly Interfaces, which is an IDL and ABI, Wasmer containers, custom container format, and the Wasmer registry. So who has heard of WebAssembly? And keep your hands up if you kind of know what it is. Okay, most of you. So I can go through this pretty quickly. So WebAssembly is a low-level binary code format. It comes with a secure sandboxed execution model, meaning the code you run in WebAssembly can't interact with the memory, even if it runs in the same process. It can't touch your main memory, it can't do anything, and it can't interact with the operating system or anything else unless you allow it to do so, unless you give it the capabilities and permissions to actually do so. WebAssembly can be really fast, like within a few % of natively compiled code, if things go well. There are cases where it can be quite a lot slower. But for a lot of use cases, WebAssembly is more than fast enough. I'll go into some drawbacks later on, but and WebAssembly is a pretty odd name for this whole thing, because it's not WebAssembly, it's not assembly, it's not a register machine, it's a stack machine, much like the JVM, so it's much higher level than regular assembly, and it's not just for the web, because it's seeing a lot of usage in plugin systems, both for editors or for proxies, and it's increasingly also making its way into cloud computing. So how it works actually is you have write code in some language, C, C++, Rust, Python, Go. A lot of languages are starting to support WebAssembly, and then you compile your code into a WebAssembly binary. And then you use a runtime to actually execute that code. And this is where Wasmer comes in. So we are building a WebAssembly runtime, but we are absolutely not the only one. Like every browser is a WebAssembly runtime. Node can execute WebAssembly, and there are also a bunch of other native WebAssembly runtimes, like Wasmtime, like Wasmer Edge. So there are quite a few alternatives. There are also interpreters that make it fast and easy to interpret. Don't have time to go into the details here, but a lot of the current runtimes also do ahead-of-time compilation to get really fast execution. So, so much for WebAssembly. The next component we're building on is WAI, or WebAssembly Interfaces. And we have to thank Lynn Clark, Code Cartoons, and Mozilla for this lovely graphic. But so what WAI is? Okay, so we want to make different languages talk to each other. What do we need to make that happen? So we need some way for them to communicate. I mentioned this before, the ABI. So a way to represent types and to call functions between different languages. And we need a way to describe our interface. And then what we get is the ability to write code in one language and call that code, use that code from another language. And an interesting property here is that you can interact between WebAssembly and normal code. So you could write something in WebAssembly, expose functionality, and then you can use that functionality from JavaScript or from Rust. But you can also write something in WebAssembly and consume it from another WebAssembly module, like something else compiled to WebAssembly. Or you could expose functionality natively and use that from WebAssembly. So that's probably a bit confusing, but essentially what it means, it enables a very flexible system where you can define a functionality you want or provide that functionality in different ways, like with WebAssembly code, with native code, and then consume that functionality, which opens up a whole different set of use cases in both for plugin systems, ecosystems, and for execution. And these, how all of this works will become a bit clearer when we reach the demo. So what WAI actually is, it consists of three things. An IDL, interface description language, where you can describe your types, your functions, your objects or resources, like with think classes with methods, just to have a definition of how your types look like, how your interface looks like. Then it's an ABI that defines how to represent types in memory and how to call functions, how to do stuff. And then there's code generation tooling and libraries to make it easy to expose functionality on one hand, and then to generate wrapper libraries for other languages. So you can easily use them without having to do any custom mapping work that you currently have to do with C APIs, for example. So what does WAI look like? As a small example, and going back to our hash IDs example, here we define a resource hash IDs with a constructor. So that's basically a class that you can create. And then it just has a few simple methods for encoding a value and decoding a value. And you could also have freestanding functions or more complex methods. You can also return errors. I'm not going into the details here. These are just the basics. So you can write that to define your interface, define your types. There's also support for variants, so think ADTs, some types for the functional programmers here. It's a very flexible system. The main point here we want is to be able to represent most languages, or how most languages look like, and how they structure their types. And we need a sufficiently general description so we can make it work across all languages. And then there's Wasmer Pack, which is a CLI utility which takes in one of these WAI files that I just showed you and generates wrapper libraries that make it easy to consume that functionality. So is this new? Someone must have tried this before, right? And the answer is yes, of course. There is a COM, Component Object Model from Microsoft. Microsoft developers will know this. There's also Swig, which is like a cross-language code generator. And there are a bunch of others. And important to mention, WAI is actually derived from WIT, which is a larger standard. But at the moment, we deviated a bit from them to get something stable, but we will probably align with what is now called the component model and WIT later on once that stabilizes. But no need for you to worry about it if you're not into the details. The main point here is what's different. So why is this supposed to work when there are other solutions that are barely used? Well, there are two different things here. Well, WebAssembly gives us a single artifact and a single execution model that can run everywhere. Because there are a lot of WebAssembly runtimes out there, and it's even in every browser, so we can just run things with very little additional effort. And in this particular case, for us, we're also providing good tooling and direct integration into the registry. And we'll see how that works in a bit. So the third component that we use to make this happen is WebAssembly Wasmer containers, which is also a bit more related to what most of you have been talking about, the whole packaging ecosystem. Wasmer containers, it's a binary container format that is runtime agnostic. It's also not even tied to WebAssembly. It has a versioning scheme, Semver versioning scheme, and a dependency system with a dependency solver. And from a container, you can provide bindings, like the WAI definitions I showed you before. You can provide libraries, and you can provide executables and file system volumes, which give you everything you need to execute things, to depend on code, and to define what you want to run locally, in the cloud, in the browser. We also have a concept of runners, where you can have different kinds of artifacts. You can have a WASM file that's runnable. You can just execute it. But there can also be other kinds of runners, like ML workloads or a JavaScript runner. And if you're interested in this, this is quite closely inspired by Google Fuchsia, like the new operating system developed by Google. They have a very similar system. So let's open the hex editor and look inside one of our containers. We have a header that describes the various sections that are inside the container with offsets, so you can quickly open any of the containers. This is also forwards compatible. We can add different section types. Then there's a manifest. That's metadata information, like your typical package manifest. What are the dependencies? What does the package provide? Names, and so on. For WebAssembly, there are a few different components here, a few interesting ones, like what capabilities do I need to execute? Like, do I need to talk to the network? Do I need to read and write to the file system? Because that gives us a great way to sandbox execution and to tell users, hey, this code actually wants to talk to the network. Do you want to allow this or not? So it's a declarative way of specifying requirements and capabilities that you need. And you don't need to use this, like you can skip this functionality, but it is there. Okay, so, and then containers have atoms, which are executable things, can be libraries or binaries, like a WebAssembly compiled library or a binary that you can execute. And then we have file system volumes. And you might ask, why are we inventing a new container format? There's OCI. There are a few important properties we get from this. One is random file access. So the format is specified in a way that makes it really easy to have random access to files. So we can just read the volume, the header, find out where a file system volume is, find out where a file is, and then seek to it and read it. And we can do all of that just over HTTP. You just need to dump the webc file into a directory, start Nginx, and all of that works. And this gives us the ability to do partial lazy fetching, which is especially relevant both for browsers and for edge compute clouds, because it gives you really fast startup. Because what do you need to run something, like say a static web server? First, you need just the binary that actually executes. That's an atom for us here. And you need nothing else, just to start up. So we can just download a tiny, seek a little bit to find out where the atom is, download that, and once we have that, we can start executing. And then we can, on demand, fetch files that the code wants to read when they read it. And that can happen just on demand, so it gives us really fast startup and lazy fetching. And we also have content. We heard yesterday a good introduction to content addressing and content-addressed caching and storage. We also do something similar. We can do the same thing on the client, so you don't need to fetch things twice, even across different packages. And we can also do the same thing on the server side. And for that, we need a custom server implementation that does the content-addressed storage, but it's a great boon, especially for if you run a package registry or if you run cloud servers, then this is a big boon because it can save you a lot of disk space, a lot of network I/O, just shuffling things around, because a lot of packages have the same contents and the same files. Just think ML models that everyone dumps into their packages. Related to the partial fetching, we also do validation with Merkle trees. I don't have time to go too deep into this, but basically, if you trust the headers, the manifest that specifies hashes for parts of the file system volume, and then you can just fetch those files and validate them based on the Merkle tree, and you know that you've downloaded something valid if you trust the headers or the manifest. which gives you the ability to do duplication, like use different like third-party storage systems even, and still know you're getting the right thing. All right, so the fourth part in the mix is the Wasmer registry, which is a package registry. There's, sorry, which is a package registry. There's nothing too special about it. You can upload your packages to the registry, and packages are represented by containers. So you upload your container to the registry. There's a namespacing system. There's nothing really remarkable about this. What is important for the flow I'm describing here is that the registry will automatically, if your package contains a WAI bindings file, the registry will automatically generate wrapper packages. So let's say for hash IDs, if I have a WAI file in my package, the registry will automatically generate an NPM package and a Python package for me that enables everyone to use it. And you can just depend on the package hosted by our registry and just use things. So to put the whole flow together, how do you actually use this? One, you write your interface definition file, your WAI file, and define your interface. You implement the functionality in a language of your choice to actually expose the functionality. Then you compile the whole thing to WebAssembly. You publish the package to the registry. The registry auto-generates wrapper packages. And then we're good to go. Like, everyone can use the functionality in the language of their choice. So, demo time. Is this big enough to read for everyone? A bit bigger, maybe. So what we have here, and we're sticking to the hash ID example. So what we have here is what I showed you before. I write my simple definition for the API. Here I also have an example of freestanding functions that aren't attached to the class. We've seen this before, so I won't linger too long on it. But what we can now do is, since this, so I'm getting mixed up here. So the next step is to actually implement the functionality. And here we implement the functionality in Rust. And we have a very convenient way to just say, hey, I want to implement this bindings.y file. And then I just write a little bit of code to actually implement the functionality. Like we saw here, in the bindings.y file, we have basically a class with a constructor, encode and decode functions, and that's what we're implementing here. We have the encode hex functions. These are the freestanding functions, and here we have the regular functions. So this is basically just TypeScript, Java. You implement an interface. That's all. That's all. Okay, so now all we need to do is compile this to WebAssembly. Here it's cached, so it's really fast, but it's not much slower because it's a small amount of functionality. And the next step then is to write a package definition for our registry. It looks a lot like most package definitions. You can provide a README, blah, blah, blah. The important thing here is we provide a module, which is a WebAssembly file, which is what we just compiled, and we specify the bindings for this module. This is the important step, because now all we can, let's bump the version here. But now what we can do is run Wasmer publish, and it will upload. And there we go. Now it's published on the registry, and we can jump over here. And here we see the 0.6 version, published less than a minute ago. And an important point here is it shows APIs. And here it shows me it generated the JavaScript bindings, so I can just use this from JavaScript. And we have a little helper command as well to make it actually usable. So now we are getting to the interesting part. Okay, so what did we do until now? We implemented some functionality in Rust, exposed that functionality, made it conform to our interface definition, and then published it to the registry. And the registry actually auto-generated NPM package for us. So now we actually want to use that NPM package. So let's go to JS. And here I can just run Wasmer add and my package name. And I want the NPM package. And this is just a little helper. It's not really needed. But if we look at package.json, we see that we just have a new dependency that imports the whole thing. And this comes directly from our registry. Pardon? I just need to run it, and then I'm done. Yeah. So now I can just run this thing. So here, and this will look a bit better in the future, but here what I do is I import my bindings, basically, and then I construct a hash IDs class. And now I can just call the encode function on my new class. And now I'm using, from JavaScript, code I wrote in Rust, going through WebAssembly. And we can do the same thing in Python, like the registry will also generate Python bindings, and we'll add more and more languages as we go along. And yeah, I'm being rushed, sorry for overrunning, but that's it. So, and I mean, I would have a few more slides, but just to finish off, 2 sentences. There are downsides, and like it's important to be honest about them. There are some downsides, but the key takeaway is WebAssembly enables universal computation. WAI brings seamless language interoperability. The WebAssembly ecosystem is still evolving, but we're getting close to something that can be used everywhere. And you can use Wasmer now to run code in browsers, locally, on the edge, everywhere you want. And yes, I'm Christoph. Here's my GitHub. You can find me on Matrix. I shun other social media. Thank you.